This is the sixth and last video for IB Quantum Mechanics. We're going to be talking about another consequence of particles being waves. Remember, de Broglie said that particles can behave like waves, and the wavelength is given by h divided by p, where p is the momentum. And the Davis and Germer experiment confirmed that by getting interference patterns from electrons and neutrons scattered off of a crystal. And now we're going to be looking at how we can use that idea to explain why energy levels in an atom are quantized. Now, remember, quantization of energy levels means that only certain orbitals are allowed in an atom. Only certain energies are allowed to the electron. And that can be explained by treating a confined electron as a standing wave. Before we work out the mathematics on that, if you have a free electron, that free electron just looks like a normal wave, traveling one direction or the other. And that can take on any wavelength, and therefore any amount of energy. But if you trap an electron somewhere, let's say you say the electron has to be between these walls, now all of a sudden the wave has to have a value of 0 at the edges of the box, because the electron can't exist outside it. And that means that you can have a wave that looks like that, or you can have a wave that looks like that, or you can have a wave that looks like that, but you can't have any intermediate wavelengths. So it's a standing wave. Remember when we did standing waves on a string? Only certain wavelengths were allowed. And because only certain wavelengths are allowed, only certain energies are allowed. And that means quantization. And so, using the idea that particles behave like waves, we can explain, and we have kind of explained in a very hand-wavy sort of way, where the energy levels in the electron or in the hydrogen atom come from. We're not going to work out the math on that because it's incredibly difficult to do the details, but we are going to look at the very simple case called the electron in a box. And the equation governing this is called the Schroedinger wave equation. You don't really need to know what the Schroedinger wave equation is, because it's awful. But let's say that we have a box. That box has a width given by capital L, and there's an electron in it. We're trying to find the energy associated with this electron, and that's going to be a kinetic energy because the potential energy in the box is 0 everywhere. And then the potential energy would be infinite outside the box, but we're not really going to go there. The formula for kinetic energy is 1/2 mv squared, but in quantum mechanics we prefer to work with momentum rather than velocity, and so the energy then becomes p squared over 2m, where p is the momentum of the electron. We also know from the de Broglie equation that the momentum is equal to h over lambda. And so the energy then becomes, go away. The energy then becomes h squared over 2m lambda squared, and now we just need to figure out what wavelengths are allowed. And it's just like a standing wave on a string. And that means the allowed wavelengths are given by 2L divided by n, where n is an integer. And so what we do is we plug that value for lambda in, and we come up with our formula for the allowed energy, which is h squared m squared divided by 8m L squared. where L is the width of the box. And this is the nth energy level. Remember, n is an integer, and that means that the allowed energies you get are what you get for when you plug in 1 to this equation for n, and 2 for this equation, and 3 for this equation, and so on. And so we've just found the energy quantization for an electron in a box. The hydrogen atom is similar but much more difficult. And now let's do a quick example. Calculate the first 3 energy states of an electron in a box 3 nanometers wide. So remind ourselves of the equation, h squared n squared over 8 ml squared. And that, if we plug in numbers, becomes n squared times the rest of the equation, becomes n squared times 6.7 times 10 to the negative 21 joules. So E1, 6.7 times 10 to the negative 21 joules. E2 is equal to 4 times that, because 2 squared is 4, which is 2.7 times 10 to the minus 20 joules. And E3 is 9 times that, which is 6.0 times 10 to the minus 20 joules. And we could keep on going. The energy level pattern, if we draw the diagram, looks like you got E1, that's 0 energy. E2 is equal to 4 times E1. E3 is equal to 9 times E1, E4 is equal to 16 times E1, and so on. And so the energy level spacing increases as you go to higher energies because of that n squared. It's a little bit different from the way the hydrogen atom works. Now, notice what happens as you decrease L. What happens when you decrease L is that you're squeezing the electron, and the energy of the electron goes up. Because you've got L in the denominator of this equation. And that means that you have to put energy in. You have to exert a force to make the well narrower. And so whenever you have confined electrons like this, they don't like being squeezed. That's a phenomenon called electron degeneracy pressure. And we'll see that again when we talk about astrophysics. It turns out to be relevant for white dwarfs and neutron stars. So what you need to know for this video is how it is that electrons being waves results in energy quantization. You need to know that that only happens when you confine the electron in a particular space, and that it basically happens because the electron forms a standing wave. That is the last quantum mechanics for IB physics.